Welcome to the walkthrough for Assignment 1, Part B. The objectives of Part B of this assignment are to learn how to synchronize Java threads via a semaphore and a Spinlock. Videos describing Java semaphores appear on my YouTube page. There's also a video describing Spinlocks there as well. I recommend you watch all these videos to ensure you have a basic understanding of these Java synchronizers. Of course, we'll also cover these topics in class as well. In this part of the assignment, you'll use a semaphore and a Spinlock to enhance the multi-threaded implementation of the Pallet Area Simulator app that you began in Assignment 1A. Assignment 1B focuses on the Pallet Area Manager, which is an object that's used to restrict the number of beings from Middle-earth who can concurrently gaze into a fixed number of Pallet Area. If you're not yet a fan of Tolkien's Lord of the Rings trilogy, you should drop everything you're doing and read about Pallet Areas here. The Pallet Area Simulator app is packaged as a project in Android Studio version 3.x. The app itself is written in both Kotlin and Java and demonstrates many Android capabilities. For the purpose of Assignment 1B, however, you'll only need to be aware of the following three directories. The first is the manager's Pallet Area Spinlock hash map, which contains the skeletons you need to fill in, as we talk about in just a minute. There's also an app source test directory, which contains a set of JUnit tests that exercise many Pallet Area Simulator features and can be used to help test the functionality you implement for this assignment to make sure it's correct. Finally, there's app source Android test, which is an Android Studio instrumentation test that can be used to run your app automatically. As before, you'll need to open the provided Android Studio project, and once it's open and synced properly, you can run the project by clicking the green Run App button in the Android Studio IDE, which will automatically prompt you for an Android emulator to run, assuming you've already created one and installed it. Once again, if you have any problems with this, please come to office hours and we'll help you get the Android emulator running. I'll also show you shortly how to run the various types of tests as well. There's a number of to-do tasks that you'll have to implement in order to complete Assignment 1B. Once again, please do not change the overall structure of the skeleton, just fill in the to-do tasks. In particular, you need to finish implementing the to-do task for this assignment in the Spinlock hash map folder. The two files you'll focus on are called Spinlock hashmapmanager.java for one, and you'll need to complete the to-do tasks in various methods and in the class itself in order to implement the Pallet Area Manager via a semaphore, a type of Spinlock, and a hash map. The second file you'll have to implement depends on whether you're a grad student or an undergrad. Undergraduates need to implement spinlock.java by completing the various to-do tasks in methods and in the class itself in order to emulate a compare and swap style Spinlock with so-called non-recursive semantics. In contrast, students taking the class for graduate credit have to implement something called the reentrant spinlock.java class, which I'll talk about in just a moment. After you finish those implementations, you go ahead and run your program, and again, it's considered correct if all the beings successfully complete all their n iterations. So a correct simulation should restrict the number of gazing beings to the number of Pallet Area, so that if there's only 4 Pallet Area configured in the simulation, then only 4 beings should ever be gazing at the screen at any given time. While the simulation runs, you'll be able to get visual feedback showing the states of the Pallet Area and the beings, as well as the progress of the gazing that's taking place. If your implementation is correct and doesn't throw any exceptions, the title bar labels will appear as green when the simulation completes. However, if your implementation throws an exception or has problems with the implementation internally, when the simulation completes, the title bar labels will be displayed as red. Moreover, you should run the tests in order to be able to make sure that your implementation passes the unit and instrumentation tests. Graduate students have some additional tasks they have to take into account, or students who are taking the class for graduate credit have to take certain tasks into account. In particular, they need to implement the Spinlock hashmapmanager.java file to replace the Spinlock class with an implementation of the reentrant spinlock.java class, which emulates a compare and swap style Spinlock with so-called recursive semantics. We'll talk about that shortly. Undergrads are welcome to implement these features and methods, but it's not required. The skeleton code for this assignment can be downloaded from my GitHub account. Assuming that you've already set up your GitLab account, you can simply go ahead and pull the skeleton code into your repository, reading it carefully in the directories we've described, and completing the various to-do task markers. The additional work that the grad students need to do is clearly marked. This assignment is designed to help you get familiar with writing multi-threaded programs using the Android Studio IDE and core Java synchronization mechanisms. It is designed to complement the Java multi-threading mechanisms that we used in Assignment 1A. This assignment, however, doesn't require you to program any Android concurrency or communication frameworks, which we'll cover in upcoming assignments. Now that I've given you an overview of the assignment, let's drill down on the various skeletons you'll need to implement. These skeletons all reside in the Managers, Pallet Spinlock Hash Map folder. We'll start with the Spinlock Hash Map Manager class, which everyone needs to implement. This class extends the Pallet Manager and uses a spinlock, a semaphore, and a hash map in order to be able to restrict access by many being threads to a fixed number of Pallet. You'll have to provide a field that is used to implement the spinlock. This spinlock, in turn, will be used to ensure that threads serialize on the critical sections we'll look at below. There's two different spinlock implementations. One, which is the spinlock class, which undergrads have to implement, and the other is the reentrant spinlock class, which students taking the class for grad credit have to implement. In either event, you need to define an instance of that here as a field. You'll also have to define a counting semaphore that limits the concurrent access to the fixed number of available Pallet that are managed by the Pallet Manager. I provided you an implementation of a Pallet map, which is a hash map that associates the Pallet key to a Boolean value that's used to keep track of whether the key is available. You'll see how that gets used in just a moment. There's a hook method called back called build model that's called by the framework. And this is used to initialize the various fields we just described. So we go ahead and make a new hash map. And then you'll have to call the getPallet factor method and use the result that comes back to that in order to be able to initialize the Pallet map with the appropriate values. You'll also have to initialize the semaphore to use a fair implementation in order to mediate concurrent access to the given Pallet. And finally, you'll have to implement the spinlock field. So those are fairly straightforward things to do, but you have to think through how to implement a fair semaphore. That's probably the thing that'll take little doing. Down here is the acquire method. This method is called back in order to be able to acquire a Pallet, and it's intended to block until one is available if there isn't one available right away. So the way this works under the hood is you'll use the semaphore in order to uninterruptibly acquire a Pallet, or rather, let me rephrase that, in order to wait until there's a Pallet available. And then you'll use the spinlock in order to ensure that only one thread at a time can actually come in and check the hash map to find the first key whose value is true. And this, of course, has to be done with the lock held so that you don't end up having race conditions when concurrent threads would update and access the hash map simultaneously. Once you found a free Pallet in the hash map, then you need to set its value to false to indicate that it is not available. And then that Pallet will be returned to the client and you'll release the spinlock. All the code I just described needs to go here. There's also a little check, sort of a sanity check at the bottom of this method that will throw an illegal state exception if something went wrong. So make sure that you return properly, and if things go awry, make sure you go down here to throw this illegal state exception. Here's the release method. The release method is, of course, the inverse of acquire. It's intended to return the Pallet back to the Pallet Manager, so it's available for other beings to use. And the way this works is the Pallet is passed back in. You'll need to be able to use the spinlock in order to make sure you have exclusive access to the hash map. Go ahead and change the value in the hash map, set it to true, saying it's now available for reuse, and then you'll release the spin lock, and then you'll also go ahead and increment the semaphore to indicate that there's now a possibility for another thread to go ahead and get access into the Pallet Area Manager if there was a contention for the number of beings that were currently gazing with the limited number of Pallet Area. So those are the methods that you have to go ahead and implement. Here's a little hint. I call the field M available Pallet Area. That's just the name that I used. Up here, when I defined this, you could call it something different if you wanted to, but that was what I happened to call it. So probably wouldn't be a bad idea to use the same name. It's currently colored in red because I have taken that definition out, so you'll have the fun of figuring out how to do the implementation yourself. Let's go take a look at the skeleton for Spinlock. This is what the undergraduates have to implement. So the Spinlock is used to emulate a compare and swap style Spinlock with so-called non-recursive semantics. That means that once a thread acquires a lock, it cannot reacquire the lock unless it releases it first. The way you're going to do this is you're going to use something called an atomic Boolean, and that has a method called compare and set, and the default state of the spin lock should be unlocked. So you'll have to go ahead and define an atomic Boolean with those properties set here. There's a method called Trilok, which is used to do a non-blocking acquire, so you'll have to go ahead and use the atomic Booleans compare and set method correctly here to do that check. The main method that you'll use is the one that's called lock. This is the one you have to implement. This is used to check to see whether or not the whether the lock is available. And if it's unlocked, then we're going to atomically lock it and then return. If it's already locked, we're going to continually spin, waiting for another thread to release that lock. So that's where you're going to have to use the atomic Boolean compare and set operation in order to do that. And there's a method, there's a field rather called mOwner, which is what I called the atomic Boolean. So I called it mOwner for lock owner. And this describes how you'll need to do this. You'll need to have a loop here that keeps trying to atomically set the value to true. And you should also, each time you try and fail, you should also check to see if a shutdown has been requested. And if it has been requested, then you want to go ahead and throw a cancellation exception. So you're going to check to see whether cancellation has been requested, and if so, it'll shut it down. Unlock will simply atomically set the Boolean to be false. In other words, it's now available for use. So you'll have to do an atomic operation. Of course, everything on the atomic Boolean is atomic, but you'll have to call the appropriate method to set the value of the lock to be false, which means it will be released. So we'll talk about how spin locks work in class, but these are basically the things you'll have to implement in order to make this work properly. Let's take a look at what the grad students have to do. The grad students have to implement a spin lock that has so-called recursive semantics, which we call reentrant. So a reentrant spin lock is like a spin lock, but it has this reentrant property. And all that means is that if a thread currently owns the lock, then it can reacquire the lock, simply incrementing a recursion count without having to release it first. So it makes it recursive. So basically, what you're going to have to do here is define an atomic reference that's used as the basis for the atomic compare and swap. And the default state of the spin lock, of course, should be unlocked. Now, the way you're going to do this is we're going to actually keep track of the thread ID that's the current owner of the lock. And so you'll have an atomic reference that's parameterized by thread. You'll also have to define a field that will count the number of times the owner thread has recursively acquired the lock. And so it just has to be a simple count, nothing fancy here. You can use an int, for example, as long as you give it the right default value. Over here, you have to implement the Trilok method. This is the one that's used for non-blocking acquisition of the lock. And what you'll have to do there is fill in the value to basically try to set the owner's value, which this is the owner of the reference, to the value of the thread, which is considered true. And this will succeed if and only if the current value is null, which indicates false. So that's just sort of a one-liner. Down here is really the workhorse method. This is the lock method. Similar to the one that the undergrads have to implement, the main difference here is that you'll have to get the current thread, and then you'll use the thread reference in order to be able to try to set the value of the atomic reference to the current thread reference. And that thread reference, of course, will be non-null. And so you'll have to keep checking to see whether or not you can atomically do compare and set to set the value of the atomic reference to the thread reference, and then check to see whether it's null. So you'll have to figure out how to do that. Once again, you'll have to check each time you fail to do the set atomically, when you fail to get the exclusive access, to check to see if you've been canceled or not. And then if you haven't canceled, you have to throw a cancellation exception. Unlock simply goes ahead and sets the value back to null, the value of M owner, which is the atomic reference, back to null, but only if the recursion count is going to be equal to 0. If the recursion count is greater than 0, and the calling thread, the thread that calls on lock, is the one that currently owns the lock, then simply the recursion count is decremented by 1. So only when the count is 0 and the calling thread is the thread that owns the lock will we atomically release the lock that's currently held by the owner. So those are the various classes you'll have to implement in order to be able to do this part of the assignment. The key thing you'll be learning here again are semaphores in order to be able to mediate access to shared resources concurrently, as well as spinlocks, which are used to guard critical sections from simultaneous access in order to be able to prevent race conditions. Now that we've had a chance to look at all the skeleton code, let me show you how to run the various tests. We'll look first at the unit tests. These are JUnit tests that use Mockito to do various types of white box and black box testing. So we come over here and we right-click on the menu item under the simulator package, and then we click Run Tests in Simulator. So you can see it goes ahead and builds the test. Now it's running the tests. As you can see here, there's a bunch of different tests. There are tests here that exercise the same functionality that you did for assignment 1A. There's also a whole bunch of new tests that exercise functionality that you're doing for assignment 1B. And if all goes well, and you can see here it's all gone well, then everything should be green. If for some reason things don't work properly, your implementation has a bug or a defect that we can detect through the tests, then you'll see these being either red or yellow, or maybe it's orange. But in any case, it won't be green. So everything should be green if all goes well. Always keep in mind that testing can't detect the absence of bugs, just the presence of bugs. So just because all the tests pass doesn't mean your code is perfect, but it's certainly a good indicator that it's probably doing fairly well. There's another type of test that you should run to make sure your program is working properly. These are the so-called instrumentation tests. They're over here in the Android test package. What you do here is you right-click on this and do Run Tests in EduVandy app. This will go ahead and prompt you to run an emulator. I've already got one up and running. If you don't have one, it'll go ahead and launch it. You can see that here's the emulator over here. If we take a look, you can see it's going to start running it. It's running it in something called performance mode, which, as you'll see in a second, goes very quickly and does a stress test of your application, trying to make sure that it's running properly. You can see that there's some statistics that are showing up there. Oops, we'll show those in a second when it rotates back around. It's also demonstrating how the program works properly even when screen rotation takes place. If you take a look at the top part in green, you can see it has 10 beans and 6 Palantir. And it's going to run, in this particular case, 10 iterations. And it'll keep track of how many of these iterations are completed properly. It also keeps track of how long it takes to run the various tests. So this will just run for a while and kind of stress things out. If things go wrong, you'll get red icons or red text at the top title bar. It's also worth taking a look at the Logcat output. if you are having problems. These are diagnostics that are being presented by the underlying Android system, and there's actually debugging information that comes through from the app as well. So as you can see, this particular stress test worked properly, so everything went well. And if something had gone wrong, you would have seen it because it would have shown up with red text instead of green text when things were done.